Welcome everyone to the second talk in the second series for Vantage. And today we're very happy to have Francesc Vite speak about Sato-Tate groups of abelian varieties of dimension up to 3. One request before we get started is for everyone to turn off your video because that makes it easier to put the recording on YouTube afterwards. And Francesc, is it okay for us to put this talk on YouTube afterwards?
Yes, that's okay.
Yeah, great. Well, go ahead.
Okay. Well, first of all, thank you very much, Rachel and Drew, for making this virtual seminar possible. I think the mathematical community really appreciates that in this time we can still exchange mathematical ideas and mathematical knowledge. Thank you very much, Rachel, for inviting me to take part in this series of 5 talks devoted to generalized forms of the Sato-Tate conjecture. So after Kiran's overview talk, today I will concentrate on the classification of Sato-Tate groups of abelian varieties of dimensions 1, 2, and 3. And I will first start by re-examining in detail the Sato-Tate conjecture for elliptic curves. And while doing so, I will review some basic notions on equidistribution. So on this first section, I will intertwine slides regarding the Sato-Tate conjecture and slides recalling some basic notions on equidistribution. Then I will state the Sato-Tate conjecture for abelian varieties, but I will do so without giving a formal definition of the Sato-Tate group. Rather, I will just present some properties that the Sato-Tate groups of abelian varieties of dimension up to 3 satisfy, and this will be enough for our purposes of classifying Sato-Tate groups of abelian surfaces and abelian threefolds. To get the actual formal definition of the Sato-Tate group, you will have to wait till the 4th talk in this series of talks of David Ziwina, so that we can keep your thrill high till then. So let's start with elliptic curves. So K will be a number field throughout the talk, and let E be an elliptic curve defined over this number field. And then for every prime of good reduction of the elliptic curve E, we will be concerned with the quantity AP, which denotes the difference between the absolute norm of P plus 1 and the number of points of the reduction of the elliptic curve modulo P. And I will call this quantity the Frobenius trace, because it's just it's the trace of a Frobenius element acting on an analytic Tate module of E. And now the Hasse-Weil bound tells us that if I normalize the Frobenius trace by dividing it by the square root of the absolute norm of P, I get a quantity that lives on the interval from -2 to 2. I will denote these quantities, the normalized Frobenius traces, and we will denote them by AP bar. And the Sato-Tate conjecture is a prediction for the distribution of these normalized Frobenius traces on the interval from -2 to 2. Okay, and to speak about equidistribution, we need to speak first about measures. So let me present them on this slide. So, and I will do it in a general context that we will need later, which is that of, so let me take X a compact topological space, and let me denote by C of X the Banach space of complex value functions which are continuous on this space X. And then a measure is just the continuous linear form on this space of continuous functions C of X. So this mu just attaches to a continuous function some complex number C. And I will often just use this, the integral notation for this complex number mu of X. All the measures that we will use in this talk will be positive, and this means that they attach a positive real number to a function which takes positive real numbers and will be normalized. And by normalized, I just mean that they attach the value 1 to the function that it's constant and equal to 1, except in one place where I will need a measure which is not normalized in this way, but I will specify it. And now we want to make sense of the notion of saying that a certain sequence of elements in X is equidistributed with respect to the measure mu, or simply mu equidistributed. And by this we mean that for every continuous function on X, if we look at the limiting average of this continuous function on the sequence of elements xn, what we get is precisely the measure of the function. And to see how this formal definition matches your intuition, you might think of f as some function that approximates the characteristic functions of subsets of X. So just to see an example of this, we can take for X the interval from 0 to 1, mu the Lebesgue measure, and then by using this interpretation, one finds that a sequence of elements xn is equidistributed on X with respect to the Lebesgue measure, even only if for every subinterval of the interval from 0 to 1, the limiting proportion of elements xn which lie in this subinterval is equal to the length of the subinterval. Okay, so now let's go back to the case in which we had an elliptic curve defined over the number field E, and we had defined normalized Frobenius traces. We can put them into a sequence by taking the primes ordered by their absolute norm, and then the Sato-Tate conjecture is the prediction that this sequence of normalized traces is equidistributed on the interval from -2 to 2 with respect to a measure that takes 3 possible forms. So forms depend on E. If E does not have complex multiplication, then the measure that we have is a semicircular measure. If the elliptic curve has complex multiplication by some imaginary quadratic field that happens to be contained in the ground field, then we get a U-shaped measure. That's the second case. And in the third case, which corresponds to the situation in which E has complex multiplication by some imaginary quadratic field, which is not contained in the field of definition of the elliptic curve, then this measure has two parts. The first part is a Dirac measure at 0 of mass 1/2 that accounts for the fact that for this kind of elliptic curves, half of the Frobenius traces are 0, and a second part of the measure, which is just which is again U-shaped, and it's just a rescaling of the measure that we get in the second case. Okay, and maybe I should say that this conjecture is known in many cases, but Kieran already explained this in his talk 2 weeks ago. He also explained the historical context of this conjecture. And what I would like to do now is to explain the origin of these three measures. So for this, I need to go back to discussing equidistribution. And now we will restrict ourselves to the case in which our topological space is just the space of conjugacy classes of some compact group. And in this case, the functions on X are just the class functions on the group, the central functions on the group. And for such a group, so we have a measure which is invariant under left and right translations. And actually, this property uniquely determines this measure if we take it normalized. And I will denote, so this is the Haar measure, and I will denote by mu sub x the projection via the natural projection from the group to its set of conjugacy classes. And so let's look at two examples of this. First, let's look at the case in which our group is SU2. So that's the group of matrices which are unitary and have determinant 1 of degree 2, or matrices which can be written in this very explicit form, AB minus B bar A bar, and where A and B are complex numbers. And observe that for these matrices, the eigenvalues come in conjugate pairs, and they have absolute value 1. And moreover, this pair of eigenvalues determines the conjugacy class of such a matrix. So in this case, we can think of the projection map from SU2 to its set of conjugacy classes as the map that sends a certain matrix to the eigenangle theta that allows to write its eigenvalues as e to the I theta and e to the minus I theta. And then one can show that the projection on the set of conjugacy classes of the Haar measure of SU2 takes the form 2 over pi times the square of sine of theta, a measure that also appeared in Kiram-Stock. We can also look at the example of the unitary group of degree 1. And in this talk, I will always look at this group as embedded in SU2 in the following form. So this is the group of complex numbers of absolute value 1, and I look at this group inside SU2 by sending such an element of absolute value 1 to the matrix made of this element 0, 0, and its complex conjugate. And this group is abelian, therefore it can be identified with its set of conjugacy classes. And in this case, the Haar measure is really easy. It's just a uniform measure because we can identify this group with a circle, and the measure should be invariant under rotations of the circle, so it should be the uniform measure. Are there any questions so far?
Feel free to use the chat window to write your questions if you don't want to speak out loud. Or you can speak out loud, whichever is easier for you.
Okay, so yeah, this is the frame in which I will state the Sato-Tate conjecture for abelian varieties. So now let A be an abelian variety defined over the number field K and of dimension G. And let me denote by rho L its L-adic representation. That's the representation that encodes the action of the absolute Galois group of K on the L-adic Tate module of A. And then the generalized Sato-Tate conjecture, the Sato-Tate conjecture for abelian varieties, predicts the existence of a certain compact subgroup of the unitary symplectic group of degree 2G, and the existence for each prime of good reduction of the abelian variety of a conjugacy class in this group G, with the property that its characteristic polynomial coincides with the characteristic polynomial of the image of a Frobenius element at P by the aladic representation attached to A, normalized dividing by the square root of the norm of P in the same way as we were normalizing the Frobenius traces in the case of elliptic curves. And with this compact group and this set of conjugacy classes in this compact group, which can be put in a sequence by ordering the primes by absolute norm, have the property that this sequence should be equidistributed on the set of conjugacy classes of the group with the projection on this space of the Haar measure of the group. And well, I should say that Serre makes this conjecture somehow more specific by giving an explicit candidate for this group G, which is the Sato-Tate, which we call the Sato-Tate group of the abelian variety A. And it's also worth mentioning that when the dimension is at most 3, Banashak and Kedlaya can define the Sato-Tate group of A purely in terms of endomorphisms. According to this definition, one sees very easily that in the case of an elliptic curve, then the Sato-Tate group has 3 possibilities. 2 are groups that we have already seen in previous slides. It is SU2 if the elliptic curve does not have complex multiplication. It's U1 if it has complex multiplication over the ground field. And it is the normalizer in SU2 of this U1 that we saw embedded in SU2 in the case that complex multiplication is not defined over the ground field. So note that this third group is no longer connected. The connected component is U1, but then we have a second connected component generated by this matrix 0, 1, minus 1, 0. And the projection via the trace map of the Haar measures of these groups are the measures on the interval from -2 to 2 that we saw on the slide concerning the Sato-Tate conjecture for elliptic curves. Okay, so let's go back to the general situation. So we have a natural map from the set of conjugacy classes of the Sato-Tate group to the set of conjugacy classes of the unitary symplectic group. This latter set consists on the set of characteristic polynomials of its element, the elements of USP2G, and then this map takes the form of sending a conjugacy class in the Sato-Tate group to its characteristic polynomial. And this map is in general not injective. So yeah, so looking at the distribution of characteristic polynomials is just a slightly weaker form of the precise general Sato-Tate conjecture. However, it's interesting to study this weaker form because it's more amenable for computation, and it's the one that one uses when one wants to do numerical verifications of the Sato-Tate conjecture, as we will see in 2 weeks in Drew's talk. So let me comment about this weaker form. If one is only interested in the distribution of characteristic polynomials, then one can capture their distribution in terms of the moments. So I will define what I mean by the moments of of a group. So now let's take G some compact group, the unitary symplectic group. Let me denote by X its set of conjugacy classes. And now having this G as a subgroup of the unitary symplectic group endows us with a tautological character. So that comes directly from this inclusion of G in USP2G.
Oh, Francesc, there's a question, by the way, in the chat.
Yeah. Oh, let me see.
You want me to read it to you?
Yeah, can you read it for me?
Yeah. Are conjugacy classes in USP2G completely determined by their characteristic polynomials?
Yes, there's a bijection. We can take this as a fact. It's not the case for the conjugacy classes of the Sato-Tate group or another subgroup of USP2G, but that's the case for USP2G. Okay, so I had some given group in the unitary symplectic group equipped with its tautological representation, and I wanted to define moments for it. So for this, I take some non-negative integers n1 to ng, and then the corresponding moment to this table of integers is the average of the product of the respective powers of the first half of the coefficients of the characteristic polynomial of a random element in G according to the Haar measure. That's what this integral means. And this captures the distribution of characteristic polynomials because the first half of the coefficients of the characteristic polynomial of an element in USP2G determines the whole polynomial, and the distribution of this first half of the coefficients of this G tuple is determined by these moments. And an important comment here is that the expected value of a character, according to the Haar measure, the measure of a character, is just the multiplicity of the trivial representation inside of the character. So this means in particular that these moments are non-negative integers. So let's compute them in one example. So let's take G as U2. Then I need to recall that the irreducible characters of SU2 are the symmetric powers of the tautological representation. So let me denote by high sub n the nth symmetric power of the tautological representation, and then it's well known that that in terms of the eigenvalues of an element in SU2, this character high sub n admits this expression, this well-known expression. And okay, and now we will apply the formula for the moments that I wrote on the top of this slide. So the two, now we are in a situation of in which G equals 1. So the 2nth moment of SU2 is just the multiplicity of the trivial representation in the 2nth power of the tautological character. And now, well, applying the binomial theorem and writing this tautological character as a sum of its two eigenvalues, we can find an expression of high to the 2n in terms of the irreducible characters of SU2, and we can write this high to the 2n as a linear combination of irreducible characters with integral coefficients. And now the multiplicity of the trivial representation is just the coefficient of the trivial representation in this expression, it is this difference of consecutive binomial coefficients, which we can simplify, and we get the nth Catalan number. So they're integers, and they're very nice integers in the case of SU2. And actually this same argument shows you that the odd moments of SU2 are 0. Okay, so I think with this I've said all I wanted to say about elliptic curves and basic notions on equidistribution. Maybe it's a good moment to pause for some questions. Okay, well, if there aren't any, then I will move on.
Yeah, thanks. It seems like it's going very well.
Okay, thank you. Okay, so now I will, I will present these properties that saddle-tate groups satisfy for abelian varieties which are of dimension at most 3. So from now on, A will be an abelian variety of dimension at most 3. And I already mentioned before that in this case, Banashak and Kotlaya describe the saddle-tate groups, the saddle-tate group purely in terms of endomorphisms. And moreover, they provide us a list of properties that, that this group satisfies in this situation. And so I will list these 4 properties. So the first property is the so-called Hodge condition. So and this asserts that there exists some homomorphism from the unitary group of degree 1 into the connected component of the identity of the saddle-tate group that sends a complex number of absolute value 1u to a matrix which has g eigenvalues equal to u and g eigenvalues equal to the complex conjugate of u. And we call the image of any such homomorphism a Hodge circle. And the Hodge condition, moreover, states that the subgroup generated by all Hodge circles is a dense subgroup of the connected component of the identity of the saddle-tate group G naught. Okay, and well, this property, while not known in general, it's expected in general, and it's a consequence of the validity of the Mumford-Tate conjecture. The second property that saddle-tate groups up to dimension 3 have is the so-called rationality condition. This condition says the following. So take some random character and some random connected component of the saddle-tate group, then the expected value of this character over this particular connected component should be an integer. So if I took the average over the whole group, then this is automatically an integer. But here we are requiring this this more restrictive condition that it's the average over every of the connected components of the group is an integer. And here it's the point where I make the exception of not taking the hard measure normalized so that the measure of the group is 1. We need to normalize the measure to make sense of this, so that the measure of each of the connected components of the group is 1. or in other words, that the measure of the whole group is the index of G naught in G. And this condition is also expected to be satisfied in general. And I should also comment here that that already these two conditions, if you fix one dimension G, limit the possibilities of the Sato-Tate group to a finite list. However, this is not, this allows for more groups than we want, and at least in dimensions from 1 to 3. And in this case, we can add further conditions that will limit the list of Sato-Tate groups. And these are the following conditions. So there are two more. So for the third condition, consider the space of matrices which commute with all the elements in the connected component of the Sato-Tate group. This is a space that should mimic the geometric endomorphism ring of the abelian variety. And then if we look, so then the Lefschetz condition says that if we look at the subgroup of the unitary symplectic group made of elements that commute with all the elements in this subspace of endomorphisms E, we should recover again the connected component of the identity of the Sato-Tate group. So shortly put, the connected component of the identity should be its own bicommutant. And finally, we have the third condition. For this, let me define F to be the minimal extension over which all the endomorphisms of the abelian variety are defined. It is easy to see that this is a finite extension and a Galois extension, which I will call the endomorphism field of the abelian variety A. Then it happens that the group of connected components of the Sato-Tate group is isomorphic to the Galois group of the endomorphism field. And none of these two conditions is expected in general. So there are examples of Shioda and Manford for which the Lefschetz condition does not hold. In particular, Manford has constructed examples of abelian varieties of dimension 4, which have a trivial endomorphism ring, but for which the Sato-Tate group is not the whole unitary symplectic group of degree 8. And it is, it's an easy exercise to show that there are only 3 subgroups of the unitary symplectic group of degree 2, which satisfy all this list of properties that the Sato-Tate group has, and to which I will refer as Sato-Tate axioms, because we can think of them in this way. And actually, in this situation of dimension 1, there are only 3 closed subgroups of USP2 that satisfy the Hodge conditions. So all the others are redundant. Maybe it's a good moment to pause for some questions regarding the Sato-Tate axioms.
Hey, this is Jeff. In order to make sense of the Hodge condition and the density, do we need a Q structure on the groups, or is everything happening for complex groups?
No, it's at the level of complex groups. Of course, it comes from so when you show that they have that abelian variety that have this property, it comes from something algebraic. But it's a good question, because it's maybe something that I should have mentioned here. But this first axiom is something that only concerns Lie groups.
Oh, and it's all the Hodge circles. Okay, sorry, got it.
And in fact, the first 3 axioms are something that only concern Lie groups. So you can present them in some group theoretic way. it is the fourth axiom that involves thinking of an abelian variety behind the group. And that's why in the paper we have formulated this in a different way. You can do an analysis which concerns only Lie groups and which involves the first three actions, and then you look which groups you can realize by abelian varieties, and then you impose this fourth condition. But yeah, for the purposes of this talk, I thought I would unify all of them in four properties.
Awesome, thanks.
Okay, so now we move on, and we will analyze which groups we obtain in dimension 2 and 3 when we impose these four conditions. So I will first deal with the case of abelian surfaces. In fact, we do not only want to classify groups, we would also like to link these Sato-Tate groups to the arithmetic, to the geometry of the abelian varieties. And to do so, I need to introduce the notion of the Galois endomorphism type. I do it for an abelian variety over a number field in general. And so this notion consists of the following data. On the one hand, you have the isomorphism class of the R algebra that you obtain when you tensor the geometric endomorphism ring of A with R. And then you equip this R algebra with an action which is compatible, which is essentially the action of the Galois group on the geometric endomorphism ring. So and this action of the absolute Galois group factors by definition of the endomorphism field by the Galois group of the endomorphism field over the ground field. So it's an R algebra equipped with the action of some finite group. So let's look at the example of elliptic curves. It's easy to see that in this case we get three possible Galois types. So if the elliptic curve does not have complex multiplication, then the Galois type is just R equipped with a trivial action. If it has complex multiplication defined over the ground field, it's C, again equipped with a trivial action. And if the elliptic curve has Cm but not over the ground field, then the Galois type is C equipped with an action by the action of complex conjugation. So we get a matching of Galois types of elliptic curves, Sato-Tate groups of elliptic curves. Now I can state the theorem concerning the classification of Sato-Tate groups of abelian surfaces. That's a joint work with Kiran Kadlaya, Victor Rogier, and Andrew Sutherland from 2012, in which we show that up to conjugacy, exactly 52 subgroups of the unitary symplectic group of degree 4 satisfy the four properties, the Sato-Tate axioms that I explained in the previous section, and that all of them, all the groups satisfying these properties occur as Sato-Tate groups of abelian surfaces over a number fields. Then if you restrict the ground field to BQ, what we show is that only 34 of these 52 groups occur as Sato-Tate groups of abelian surfaces defined over the rationals. And finally, to understand the matching of Sato-Tate groups with the arithmetic of the abelian surfaces, we show that the Sato-Tate group and the Galois endomorphism type of an abelian surface determine each other uniquely. So I will now yeah, give an overview of the proof of this theorem. So one does the following. So the first step consists in classifying the possibilities for the identity component of G. And there were two axioms related to the identity component. One was the Hodge condition, the other one was the Lefschetz condition. It turns out that in dimension 2, the Hodge condition suffices. So the Lefschetz condition is redundant in this case, but it won't be in dimension 3. And one obtains 6 possibilities for this identity component. So one gets the whole USP4, and the other possibilities are just products of things that we had seen in dimension 1. So there is this subindex 2 here. This just means that we need to take SU2 embedded in USP4 by means of the 2-diagonal embedding. And then in the second column of the table, you can see the possibilities for the real endomorphism algebra of an abelian variety having a Sato-Tate group with each of these possible connected components of the identity. And now one faces the problem of computing the possible extensions of these identity components. And to do so, the first step is to compute the quotient of the normalizer by the identity component. And one does so because one can establish a bijection between the Lie groups that extend G0 with the finite groups in this quotient. So one turns a Lie group, a theoretic problem, into a group concerning finite groups. And observe that some of these quotients are infinite groups, so they contain infinitely many finite subgroups, and what will limit the possibilities to a finite list is imposing the rationality condition. So let me denote by curly A the set of finite subgroups in this quotient for which the rationality condition is also satisfied. This limits the possible orders of these groups and ultimately leads to a finite list of possibilities. And the last column of this table lists the number of possibilities in each case. And if you add all of them up, you get 55 possible extensions, which exceeds in 3 the 52 groups that you saw in the statement of the theorem. These 3 extra groups that all occur in the case in which the connected component of the identity is the product of U1 cross U1 happen not to satisfy the Serre axiom. So, and how does one show that? One does the following. So first note that this possibility for the identity component corresponds to an endomorphism algebra tensored with R, which is C cross C. And this means precisely that up to Q bar isogeny, A is the product of abelian varieties with complex multiplication. Okay, yeah, and that's a rather conspicuous way to say that A is either an abelian surface with complex multiplication by some quartic CM field or the product of 2 CM elliptic curves. Now we impose the Serre axiom. So the group of connected components of G should be the Galois group of the endomorphism field. But now we are in a CM situation, and Shimura tells us that we can express this Galois group of F over K as a product of Galois groups of the respective reflex CM fields, of the CM fields of the factors of A with complex multiplication. And then an analysis of this possible reflex CM fields leads you to the possibilities to a list of possibilities for this product of groups, and they should be subgroups of C2 cross C2 or C4. And note that this is much more restrictive than just being a subgroup of D4, which was the value for the quotient of the normalizer and G0 that we had obtained in this case. So this rules out the three spurious groups. And yeah, maybe it's a good moment to ask to pause for some question regarding the classification in dimension 2. Okay, so if there aren't any questions, then, well, I should say that this only addresses the classification of groups. Now one has to realize all of them by abelian surfaces, but I will not say anything about this in this section. If time permits, maybe I'll say something in dimension 3 to which we will move next, but not yet. First, I want to make 3 additional I want to mention 3 disconnected facts. So I remark a corollary of this classification and a theorem. So the remark is that if we let G run over these 52 groups that we obtain, then we find that the sequence of moments, we are in dimension 2, so now it's indexed by 2 numbers, by the first 2 coefficients of the characteristic polynomial. Then the sequence of moments attains 52 values. In other words, this means that distinct groups yield distinct distributions of characteristic polynomials. The second fact is a byproduct of the classification, which I make to emphasize on the comment that understanding, so classifying Sato-Tate groups is an interesting task per se, but it also provides some basic knowledge on the arithmetic and the geometry of abelian varieties. And for example, from this classification, we obtain that the endomorphism field of an abelian surface defined over a number field has a degree that divides 48. And this improves some previous work by Silverberg. And the final thing I want to mention is regards about what is known about the Sato-Tate conjecture in dimension 2. And well, I put together the work of Kristin Johansson from 2014 and that of Noah Taylor from last year. And by putting the 2 of them together, what one sees is that that the Sato-Tate conjecture in dimension 2, and when the field of definition is the field of rational numbers, holds for any abelian surface which is non-generic. Or in other words, the Sato-Tate conjecture holds whenever the Sato-Tate group is distinct from the unitary symplectic group of degree 4. This, the case of USP4 seems out of reach with the current technology. So now let's move to abelian threefolds. And in this case, the result, together with Karen Catlaya and Andrew Sutherland, is the following. So there are exactly 410 subgroups of the unitary symplectic group of degree 6, which satisfy the 4 Sato-Tate axioms, and all of them arise as Sato-Tate groups of abelian threefolds. Before explaining some aspects of the classification, let me derive a corollary analogous to the one we saw in the case of abelian surfaces. And so that corollary is a control on the degree of the endomorphism field of an abelian threefold. And what we obtain is that it should divide 192 or 336 or 432. And this, in fact, matches with previous work of Kuralnik and Kedlaya, where they obtain a sharp multiplicative upper bound for this degree, which happens to be the lowest common multiple of these three numbers. Okay, so let's move to look at some aspects of the classification, and one proceeds formally in a similar way. The first step consists in classifying the possibilities for the connected component of the identity. Now one uses the Hodge condition, but also the Lefschetz condition. The Lefschetz condition rules out some groups. And what we obtain, so we obtain two new groups, USP6, U3, and then products of groups that we have seen already in the classifications in dimension 1 and 2. Let me make some comments on the notations. So we see U3 embedded in USP6 in a similar way as we saw U1 embedded in USP2. The subindices mean, again, diagonal embeddings. Now we do not only have two diagonal embeddings, there are also three diagonal embeddings. And most importantly, we need to think of these groups not merely as abstract groups, but as groups embedded in USP6. And in particular, see that there are two groups that are written in red, which are isomorphic as abstract groups, but which are distinct as subgroups up to conjugacy in USP6. And now, once we have the possible connected components of the identity, we need to build extensions. And yeah, for this one proceeds in a similar way as in dimension 2. One computes the quotient of the normalizer by the identity component, and one gets this list of possibilities. But fortunately, one does not have to redo the analysis from zero. In fact, so the first two cases, USP6 and U3, are trivial, and the next 8 can be more or less recovered from the analysis done in dimension 2. Because in this case, the normalizers of the factors of appearing in this connected component of the identity have the property that their product is the normalizer of the whole connected component of the identity, and one can reuse this to obtain the classification from what is known in dimension 2. The three essentially new cases are the four bottom ones, this triple product of SU2, the triple product of U1, and the three diagonal embedding of SU2, the three diagonal embedding of U1. Of these four cases, the first three are of a complexity similar to the one encounters in dimension 2. It is the last case, the three diagonal embedding of U1, that corresponds to abelian threefolds, which are cubes of elliptic curves, the most difficult one. This gives rise to 171 extensions that also satisfy the rationality condition. And in fact, it's more complicated than all the other cases together. And yeah, one could devote one talk to just explain this case. Okay, and now if you add all these numbers here, instead of 410 groups, you will get 433, which means that we are again getting some spurious groups, which we will rule out by invoking the fourth Sato-Tate axiom, the one that describes how the group of connected components of the Sato-Tate group looks like. And so, yeah, these spurious groups come from this product of SU2 with a double product of U1 and the triple product of U1s. So in the first case, what we get is just a mere reflection of the three spurious groups that we got in dimension 2. It's just that case embedded in dimension 3. For the triple product of U1s, well, you need to make a new computation, but the argument in the idea behind the argument is exactly the same. This case corresponds to a product of CM abelian varieties, and this gives you a control, a more strict control on the group of connected components of the Sato-Tate group than just the one provided by the fact that it's a subgroup of the quotient of the normalizer by the connected component of the identity. So in the first case, we roll out 3 groups. In the last case, we roll out 20. And this leaves us with for the 410 groups in the statement of the theorem, of which 33 are maximal if one fixes the connected component of the identity. Of course, there's just USP6 as an absolute maximal one, but here we mean maximal with respect to inclusions of finite index, which amounts to the same as saying maximal for prescribed connected component of the identity. And now we get some discrepancy with what we saw in dimension 2. So in dimension 2, the sequence of moments was attaining 52 values for the 52 different groups. Now the sequence of moments attains only 409 values for the 410 groups. This means that it conflates 2 groups, which are in fact very distinct. Their groups of connected components are not even isomorphic as abstract groups. So this means that, the distribution of characteristic polynomials for these 2 groups will look the same, even if the groups are very different. And then, the last comment here is something that I implicitly already mentioned before, which is that the group of components of these groups can be really big. It can attain the values 192, 336, or even 432. And in the remaining minute I have, maybe I can say a little bit about how one realizes these groups. So what we do is just to realize these 33 maximal groups that I mentioned on the previous slide, because once you realize the maximal groups, then you can realize all the subgroups by means of making base change extensions. And well, for 8 of the possibilities of the connected component of the identity, one can realize these groups by just observing that one can write these groups as products of groups which are realizable in dimensions 1 and 2, and then by taking the product of the abelian varieties that realize these factors. And this accounts for 13 of these 33 maximal groups. Then we have the case of USB6, and that's the generic case. And yeah, you can attain this case by considering any genus 3 curve, which has trivial endomorphism ring, and you can give an example of such as the one I give on the slide by using Zarian's trick, for example. Then how does one realize the maximal group with connected component U3? Well, these are realized by Picard groups with maximal Alavic image. Here is one example. Then we're left with triple products and with 3 diagonal embeddings. The triple product of SU2s is realized by taking an elliptic curve defined over some non-normal cubic extension, which is not isogynous to its Galois conjugates, which is not a Q curve, and by taking the restriction of scalars down to Q. For the triple products of U1, I already mentioned that they correspond to products of CM abelian varieties, and one can arrange that so to hit the 3 maximal groups that one has in this case. And finally, for the 3 diagonal embeddings, one needs to twist cubes of elliptic curves with complex multiplication and without complex multiplication. And yeah, I think, yeah, that's the time to stop.
Oh, thank you. Let's see, are there any questions?
So what comes next?
Well, something interesting would be to work out maybe in which cases the Sato-Tate conjecture is known for abelian threefolds. Of course, then, yeah, one can also investigate Sato-Tate groups in dimension 4, but then things get much more complicated, as will become apparent after David Zivuina's talk, because then one cannot define, one cannot control the Sato-Tate group purely in terms of endomorphism. So it seems there's a lot of work there.
Thank you.
Oh, thanks. Right, go ahead.
You mentioned realizing these by base change when you have non-maximal examples. Is it clear which of these non-maximal ones are realizable over Q?
Oh, it's true. That's also an open question, and it's not clear at all. Yeah, one could also try to address this question of how many of these 410 groups can arise among abelian threefolds defined over Q. Yeah, it's unclear. It seems a difficult question. There are many cases now. Yeah, maybe I should mention that, yeah, all the maximal groups, these 33 maximal groups, can be realized over Q.
Here's a question from Heidi Goodson. For U1 cross U1 cross U1, can you take a product of 3 different CM elliptic curves, or will that just yield U1 sub 3?
Yeah, if you take a product of 3 CM elliptic curves, which are non-Q-bar isogynous with CM by 3 distinct quadratic imaginary fields, then you lie in this case, and in fact corresponds to the case in which the group of components is a product of C2 cross C2 cross C2. If you take, for example, an abelian threefold, which is the product of an elliptic curve with CM, with an abelian surface with CM by a quartic CM field, then you can hit this case, C2 cross C4. And if you take an absolutely simple abelian threefold with CM by a sextic CM field, then you can hit this group of components C6. So these are the three maximal groups that one has in this case, and one of them is in fact hit by the example that Heidi is considering.
All right, everyone, thanks so much for joining today. And the next talk will be April 21st. Drew Sutherland will be speaking about arithmetic L functions and their Sato-Tate distributions. And I hope you all stay happy and healthy until then and after. Thank you.